All right, friends, welcome back. In this video, I want to go ahead and tackle P.2 in your textbook, which is going to talk about exponents and radicals. The thing about this is that there's just so much to talk about with exponents and radicals. There's so many different properties of exponents that will take themselves into talking about radicals. So in order to save time on this video, I'm not going to meticulously go through each property and explain each one. I would really like to just get to some examples here. So very first and foremost, we'll start off with exponents. There's the quick definition of an exponent. It's just repeated multiplication. And if you study these ideas long enough, you start to notice patterns and develop shortcuts. And we call these shortcuts the properties, okay? So each one of these properties is going to talk about an exponent. So for example, this first property is going to say that if I have like bases that I'm multiplying, then I simply just want to go ahead and add those exponents together. Okay. Similarly, in this next property, if I have like bases that I am dividing, b divided by b, then I would want to just simply go ahead and write that with some subtracted exponents. So getting into these easy examples over here off to the side, I'm not going to meticulously talk about how you get these results, but I will just share with you that the result here is simply going to be 2 to the 5th, and the result here is going to be 2 to the 2nd. You may pause the video and ponder on that for a moment and think about why that is, okay? And matter of fact, on that first example, instead of just simply calling that 2 to the 5th, we could do one better and actually evaluate 2 to the 5th. That's 5 copies of 2 all multiplied together, and I definitely think that that is going to give us a value of 32. So in this class, I would like you to evaluate all the way if possible, okay? This next one down, this is kind of our more weird property. This is the negative exponent property. And so basically, we just kind of want to talk about what happens if you have a negative exponent. The way that I want you guys to think about this is that if you have something with a negative exponent, like here, a to the power of negative n, I want you to think about that as always being over 1, because I could take any number and put it over 1. And then what that negative exponent does is it makes the base on the top and the base on the bottom swap places. So this a that was on top of this fraction, that's going to swap to the bottom, and this 1 that was on top is going to swap to the top. And you can see that here. The 1 is now on top, and the a is now on bottom in the next line of my equality here, okay? And once you do the swapping, the negative exponent disappears. Okay, so we're going to go ahead and write our next line without the negative exponent on that. And then this is just an equivalent way of writing that exact same thing, 1 over a, the quantity, all raised to the power of n. And so that just gives us a really simple way of writing our negative exponents. So again, I'm not going to dwell too much on these examples here. Y to the power of negative 3. Hopefully it doesn't take a lot of convincing to see why this would just simply be 1 over y to the 3rd. I'll let you ponder on that on your own. And then we could also equivalently write this as the quantity 1 over y, all raised to the 3rd power. Okay, so two different equivalent ways of writing your answer on that one. Okay, some more properties. These say some really simple stuff. Basically, this next property says that any base to a power of 0 is always just going to be straight up 1. Fun fact, we have to make the note here that that base b could be really anything as long as that base b is not 0 itself. It turns out 0 to the power of 0 is not something that is very well defined in the real numbers. So literally anything else to the power of 0, though, is just going to be straight up 1, which is going to give us a really easy way to see why this example over here is just going to be straight up 1. Okay, because it's a whole complicated, messy expression, but I see that it's to the power of 0, so that's going to automatically mean that it's just going to be straight up 1. Okay, this next property is called product to a power. If we take the product of two bases and raise that to the power of m, then we can go ahead and say that we can replace that with the individual bases with their own exponents of m. So here it doesn't take a lot of convincing to see why this would have to be 5 to the power of 3 times x to the power of 3. And 5 to the power of 3, if you evaluate that, that's just going to be 125. And that gives us a really easy way to evaluate that example right there and get a nice answer. The next property down is called power of a power property. It basically says if I have a to the m and then I further raise that to the power of n, what I want to do is I want to multiply those exponents together, okay? And so my new exponent on that base of a is simply going to be whatever number I get whenever I take m times n. So if I have an example like this over here, hopefully it doesn't take a lot of convincing to see why this would simply be y to the power of negative 12. And my colors on my OneNote today are really giving me some trouble here. Okay, y to the power of negative 12, because that's what I get when I take 3 times negative 4. And just in general in this class, we always want to write our answers so that we don't have any negative exponents in the mix. And so we're going to apply our negative exponent rule, remembering that this is over 1, and that negative exponent makes the top and the bottom base swap places. So this is going to be 1 over, goodness, OneNote, come on now, 1 over y to the 12th. Okay? So there we go. Nice, easy result there. Moving right along, this next and last property of exponents is basically what we get whenever we take a quotient to a power. Okay, basically, guys, the way you want to think about this in general is that if you have a set of parentheses to a power, everything inside of the parentheses is going to get that power. Okay, especially if in the inside all we have is multiplication and division. If we have addition and subtraction, we're going to have to be a little bit more careful on the inside of those parentheses. But here, most of the time, we're going to have multiplications and divisions. So that's going to mean that an example like this can be handled really nicely because all I have is a simple division on the inside, no additions or subtractions. So that means everything on the inside can get an exponent of 3. And of course, that bottom we can evaluate 2 to the third power, that's just simply going to be 8, and we get this nice easy result right here, okay? So just a little bit of background on your different properties and some results that follow, some examples there, right? Your examples are going to get a little bit more complicated, so I want to kind of blaze through these as well. Here you're actually going to be given an expression, and you have to use the properties in order to simplify the expression, okay? So if you're given one like this, we have 2 sets of parentheses. Just remember that these are being multiplied together, and really every single term in the mix here is all just being multiplied. So for that reason, we can use an associative property of multiplication and pick and choose what we want to multiply. So for example, the negative 3 here, the coefficient, we can multiply that times a like term, 4, and negative 3 times 4 is going to give us negative 12, of course. Next, let's go ahead and focus on your a variables. And so we have an a right here. Maybe I can switch colors on my highlighter here. There we go. Here's an a there, and we want to multiply times a. So a times a, of course, is going to give us a squared. And then finally, we have this last type of term. We have a b there, a b to the fourth times a b to the third. That's going to give us, add those exponents because we're doing like bases of b. 4 plus 3, that's going to make 7. So nice, easy result there. Okay, the next one down, we have a set of parentheses all raised to the power of 3, and in the inside of the parentheses, the only operation that I see is multiplication. That means that everything inside the parentheses can be raised to the power of 3 without any problems. If we saw any additions or subtractions, that's where we're going to have to be a little bit more careful, but that's a later video. Okay, so in this example, we're going to have everything inside the parentheses that was being multiplied raised to the power of 3. And so this last one, y to the second, even it is going to get raised to the power of 3. And then we can clean this up a little bit according to some of our other properties and just evaluating stuff. So 2 to the third power, that's simply going to be 8. And then x to the third. And then here we have a power to a power. We have y to the second to the power of 3. And keep in mind, whenever we have that, we multiply those together. 2 times 3 makes 6. So nice, easy result there. Next one. Might seem a little bit complicated, but check it out. We've got something in parentheses all to the power of 0. And so remember that that's going to mean that this whole thing is going to go straight to 0. Okay, so maybe instead of xing all that out, I'll just say this whole thing goes to, and I think I just said a second ago that it goes to 0. I misspoke. It all goes to 1. That's your 0 exponent property, right? So this is just going to turn into 3a times 1, and that's just going to be 3a. Okay, so what seemed like a complicated problem turned out to have a nice simple result. Okay, down here on the bottom, inside the parentheses, I see that these parentheses are being raised to the power of 2. I'm checking the operations in the inside. I just see a multiplication here, and then I see a division there. No additions or subtractions to be found, so I know that everything inside the parentheses can be raised to the power of 2 with no problems. So there's the negative 5. We'll raise that to the power of 2. Here goes the x to the fourth. We'll raise that to the power of 2. And then finally on bottom, we've got the y to the seventh. We will raise that to the power of 2. Okay, so just to be clear, the whole group was being raised to the power of 2, so that means individually everything can be raised to the power of 2. And you notice that I put that negative 5 in parentheses. It's actually really important. I'm going to make the note here. Anytime that you want to take a negative number and you want to raise it to an even power, you're going to have to make sure that you include a set of parentheses around that negative number there. Okay, very, very important for purposes of being able to evaluate this in the calculator, especially for those of you who are using one of those. So negative 5 to the second power, that's going to be 25. And then these other ones here, this is just power to power. Okay, so that's going to be x to the fourth raised to the second. We're going to multiply those exponents, so that'll be x to the eighth. And then on bottom, we have y to the seventh raised to the second power. Multiply those exponents, we get 14. And there is a nice, easy result there. Okay, so working with exponents, that's what we have right there. Okay, keep in mind, this is a video, so if you guys need to go ahead and rewind and rewatch some things, absolutely you are free to do that. Okay, here in the next example, we're going to have a bunch of examples involving negative exponents. So we'll blaze through these here real quick. So the first one, it says 2x to the negative 1 power. Now, very clearly, The only base that's being raised to the -1 power is just this x. So we learned how to deal with these negative exponents, right? We're going to treat that base as over 1, and then that negative on the exponent is going to make the two bases swap places, okay? That 2 out front has nothing to do with that exponent of -1 there, so I'm just going to go ahead and carbon copy that 2 out front. But that negative exponent means that the 1 and the x are going to swap places, so I'm going to have 1 over x here. Okay, and you notice that I didn't write that extra exponent of 1 there because it would be needless. Any exponent of 1 is never needed. And then we'll just simply evaluate this and say, or not evaluate, but simplify, and say that that's simply going to be 2 over x. Okay, next one down, we see another negative exponent, but this time it's in the bottom. No problem. We know what negative exponents do. They make it swap to the reverse side of the fraction bar. So that's going to mean that the 1 on top now has a new friend. It now has x to the second to keep it company. And poor little 3 has to stay all the way down by its lonesome, okay? We can clean this up a little bit. That 1 times is really needless to write, so we're just going to go ahead and say x squared all over 3 to finish off that example. Next one down, something that seems a little bit complicated, but really easy if you take it part by part here. So let's just take this part by part. All right, let me go ahead and change the color of my highlighter here. Let's go ahead and take a look all the way to the left and take a look at these coefficients first. So I've got a 12 over 4. Okay, those are numbers that have some like factors. Okay, if I take 12 and divide it by 4, I get 3, of course. If I take 4 and divide it by 4, I get 1. Okay, and so that gives us a way to reduce those. I'll say that the 12 becomes a 3 and the 4 becomes a 1 after we divide both of those by 4. That's pretty nice. Moving right along here, let's take a look at the next one. We have our a's, right? So we have a to the third, and then we've got a to the -2nd power. Okay, so taking a look at our a's there, let's talk about how these simplify, right? Well, that negative exponent in the bottom there, remember, we know what happens there. It just swaps it to the top. So that means that on the top, we've got the a to the third that was already there, but now that negative exponent forced that a to the second to go up there and keep it company. Well, if you look at what I just wrote, that's multiplying 2 like bases of a, so we would need to add those exponents. So here that's going to be 3 plus 2, and that's going to make 5. So a to the 5th on top. Now we'll go ahead and take a look at those b's. So taking a look at b to the 4th, all divided by b. And remember, that's b to the 1st power down there. Okay, we have a negative exponent on top, and we know what those do. That flips it to the bottom. And so now on the bottom here, I've got the b to the 1st power that was already there, but now times b to the 4th power because that negative exponent brought it to the bottom. Well, I have like bases of b that I'm multiplying, so that means I need to add those exponents. 1 plus 4, that's going to be b to the 4th power. Okay, so on top, I ended up with 3a to the 5th. On the bottom, I ended up with 1b to the 4th, or in other words, just simply b to the 4th by itself. So we'll write our final result as 3a to the 5th over b to the 4th and box that as our final answer. Next one down, right? Again, these start to look a little bit complicated, but if you know your exponent rules, they don't get too bad at all, okay? I'm noticing a big set of parentheses with a big exponent of -2. We know what negative exponents do. They make the top and the bottom swap places. So that's the first thing I'm going to do here is I'm going to go ahead and swap places with the top and the bottom of this. So what was on bottom was y to the -3. What was on top was 3x to the 6th. And I'm going to go ahead and continue to write that. That negative on that exponent of 2 outside was what caused that swap to occur. So now that exponent just becomes +2. Okay, and we'll take a look at what we've got here. Well, I've got a negative exponent on the inside now, and we know what those do. That swaps it to the reverse side of the fraction bar. So I'm going to go ahead and continue to write this as, after that term swaps to the bottom, I'm going to have on the bottom here 3x to the 6th, y to the +3, because remember, once that occurs, the negative in the exponent goes away. And nothing was really left on top except an extra factor of 1 that we could have written there to begin with to see that it was there. But now, all the operations that I see on the inside, I see that big fraction division, and then I see multiplication. There are no addition or plus signs anywhere, so that means that I'm free to take this 2 and raise everything inside to the power of 2. So the 1 on top, raised to the power of 2, 3 on bottom, raised to the power of 2. I've got 6 to the x to the 6th power, I should say. Tripping over my words here. And then y to the 3rd raised to the 2nd. Okay? So again, I'm just basically giving everything that was inside of the parentheses its own exponent of 2. And then I'm just evaluating, right? Well, on top, 1 squared, that just makes simply 1. On the bottom, 3 squared makes 9. X to the 6th raised to the 2nd, that's power of a power. So we multiply those exponents. So 6 times 2 is going to make 12. X to the 12th power. Same thing for that y. This is y to the third, further raised to the second, so that's power to power. Multiply those exponents. It's going to give us 3 times 2, which makes 6. And there is our final result right there. So dealing with negative exponents, just remember, if you see that negative sign on your exponent, that means make the top base and the bottom base swap places. Very simple. Okay? Moving right along here and just simply talking about roots of numbers. There's the simple definition right there, which I will let you go ahead and pause the screen and read if you like. But basically, it's just another way to write exponentiation, right? So this is what we just finished talking about, this idea that if I've got 4 to the third power, it makes 64. Another way that we could have written that, maybe in a different language if you want to think about it that way, would be the language of roots. Maybe instead of saying 4 to the third power gives me 64, I could talk about another relationship between these numbers and say, well, if I start off with that 64, what is the cube root of 64? And I want you to remember what that means, right? If I want to write the cube root of a number, that's basically saying, what number do I need that many copies of to make a 64? Okay, so because the index on that root is a 3, that's the question that we're asking. What number do I need 3 copies of to make 64? Well, that number would, of course, just simply be the number 4. 4 times 4 times 4 makes 64, and so that means the cube root of 64 is 4. Okay? Lots of different properties involving radicals here. I'm going to blaze through these just like I did the last ones. You might go ahead and take a look at these properties and then take a look at some of these examples and reason for yourself why some of these might be true. I'm just going to go ahead and write down some of the answers for these. So for that first one, the result there that you're going to end up with is simply 8. You might pause the video looking at the property, looking at that example, and asking yourself why that might be true. Basically, on the next one, it says if I have 2 different roots that I'm multiplying, I can go ahead and write that with just 1 root, but that product on the inside. So here, the result in this next one, I will let you think about why this is the case, but the result on that would simply just be 3. You might want to think about why that's the case. On this next one, I've got the division of 2 roots, and I can say that that's equal to 1 root of the division. Okay? So for this next one, we might go ahead and say here that the result on that is going to be a 2. So if you want to pause the video and kind of go back to these examples and see if you can work them out on your own, that might be a good exercise. But again, just to kind of save time on the video, we're just going to point out these properties and use them in some further examples we want to maybe spend some more time on, but then just kind of give you these here, okay? So next up, we are going to go ahead and see here that this next example is going to have a result of positive 2. And this property basically says if I take the root of a root, then I can just go ahead and write 1 root, but the index becomes the product of the 2 indices that came before. Okay, so because this one over here would be a 2, basically what we're saying here is that this would be the 6th root of 64. Okay, and that's why that result would be a 2. For this next one, it says for a positive number a, so that means that this result works for any base number a that you would want to take a look at. Basically, this talks about inverses. It talks about how an nth root is always an inverse to an exponent of n. So that means that over here, if I have the 5th root of x to the 5th, that 5th root and that exponent of 5, those are inverses of each other, and they make each other go away, just leaving you with the base of 7 as your result there. So that's always going to be the case. But you got to be careful about whether or not that index number is even or odd, and that's what this next property talks about. So if the index is an odd number, that's when it's easy mode. That's when it just works out the exact same way that we just talked about. If the index number is the exact same as the exponent number, then they make each other go away, and you are just left with that base number, like here in this example. The result there would be -5. But the pain in the butt comes in whenever that index is even. Because if it is even, then we're starting to talk about how a negative times a negative makes a positive, and long story short, all we're going to have to do is make sure that we include an extra set of absolute value bars around that base number. So here, because that index number is a 2, and the exponent is a 2, that's an even number, my result is going to have to be written as the absolute value of -5, and that's just simply going to be +5 here. So paying attention to your index number is going to be very, very important as you start to take a look at roots and simplifying them. Okay, which is what we're going to start to do now. We're going to take expressions and we're going to simplify the radical, okay? Here's the deal here. The root that I've got here is going to be a square root, okay? So we're paying attention to the index, and it looks like OneNote is giving me a little bit of trouble. Oh, there it goes, okay. So the index here, we don't see an index number, so the assumed one is that we have an index of 2 on all of these roots. And what are we even looking at? Well, we are going to have to look at breaking up a 75x to the 9th in terms of perfect squares. Okay, so we're trying to ask ourselves, what is the largest perfect square that goes into 75? So for this, you may need to, off to the side, write down your list of perfect square numbers, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, etc., etc., etc. What you're looking for is the largest number in this list that goes into 75. And I think if you play with it a little bit, you will realize that 25 is the largest number in this list that goes into 75. And again, I'm just getting these numbers by taking each one of my counting numbers and squaring. We call this list of numbers your perfect squares. And this would be a list of numbers that I would expect you to be able to recreate if you needed to on the fly. Okay? Now, we have to break up 75 in terms of the perfect square number 25, but then times what? Well, times some sort of leftover number, and that has to be 3, because it has to be 25 times 3 that gives us the 75 there. Okay? Very similarly, we can think about how to break up an x to the 9th. We can break it up as some number of copies of x that we can easily divide by our index number, which I think the easiest case here would be to just say I could break up x to the 9th as simply x to the 8th times an additional copy of x. Okay? The reason that I might want to do that is, again, because I've got these values here that represent perfect squares. I've got 25 and x to the 8th. These are ones that I'm going to kind of group together and call your perfect square term over here. And then the other ones, the 3 and the x, those are what we might call your leftover terms. And the reason why we might break it up in this way, again, is because if we break it up in terms of perfect squares, 25 and x to the 8th, those are going to be some quantities that really play nicely with this index of 2 on my root. I could just now simply say, okay, the square root is 5, and the square root of x to the 8th is simply going to be x to the 4th. And the reason why that is as x to the 4th all raised to the 2nd power, okay? And so those would undo each other. And then because the 3x on the inside, those are not, that's just the leftover terms, we would just have to leave that underneath the radical, and this would be the way that we want to write that result, okay? So, that's a kind of a blaze through explanation of what we're doing there, but there's a lot of different resources online to teach you how to simplify radicals, and also if you need help on the concept as well. Okay, but let's get into some examples here. So example 5, we have the square root of 80 x to the 15th. We're going to break up in terms of some letters. So if you think about your list of perfect square numbers, I think the largest one that goes into 80 would actually be the perfect square number 16. Okay, now 16 times what makes 80? Well, if you play with it, 16 times 5 is going to give you 80. Okay, so again, we wanted to do that because later on we're going to have to take the square root of this number, and that's just going to simply equal 4, which is nice. Here, if we take the square root of 5, it's going to have to stay under the radical later on because that's a leftover part. Okay, this next part here, the x to the 15th, we could break that up. Remember, the index out here is a 2. Okay, so the easiest way to do this, folks, is to break it up into the largest even x you could fit into a 15, and then just say times an extra copy. Okay, so x to the 14th times x would make x to the 15th. And if we apply that index root of 2 there, then we're going to have on the outside 4, because that's what we got when we did the square root of 16. And then if we do the square root of x to the 14th, that's just taking that exponent of 14, dividing it by the index number of 2, and we get x to the 7th out here. Okay? And everything else that was inside of the radical is going to have to stay there. So namely, we're going to have 5 staying under the radical and also x. So the square root of 5x is what we are going to have to leave under the radical in that one. Okay? Next one, we're talking about a cube root now. So in order to think about how to break up your numbers now, we now need to think in terms of perfect cubes. So what is 1 cubed? What is 2 cubed? Just all of your counting numbers cubed. We're going to have to kind of think about that complete list and look for the largest one that might go into 32. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, so on and so forth. Okay? Now, you notice that these numbers get pretty big pretty quickly, and so pretty obvious way to break up a 32 in this case, in terms of your cube numbers, is to break this up as the number 8 times the leftover. Well, 8 times what makes 32? I believe that's going to be a 4. Okay, so that's how we're going to break that up. Again, the reason that we're doing that is because if you take the cube root of 8, it's going to give you a nice number. It's equal to 2. Okay? Now let's take a look at this x to the 6th. Remember, we're going to take a look at the exponent number and the index, and notice that these are numbers that play nicely together, right? So that index is 3, the exponent is 6, so we can break this up and simply just say, matter of fact, an easy way to kind of think about this would be to just say, what if I just did x to the 2nd power and square that? Or not square, sorry, cube that, right? Because we're dealing with cubes here, okay? Well, if I do that, then check out what happens. So I'm going to go ahead and break up this 32 by calling that 8 times 4. Leave a little bit of space. Okay? And then that x to the 6th, I'm going to go ahead and write as x to the 2nd further raised to the power of 3. Okay, that's all going to be inside of a cube root. So think about what we did before, right? We did the cube root of 8. That was 2, so that leaves the radical. And then think about your inverses, right? If I have a cube root of something to the power of 3, then we said before that those undo each other, and it just leaves you with this base on the inside. So what also is allowed to leave the root is that copy of x to the 2nd. And then this poor little 4 has to stay under the cube root because that's our leftover part. And we'll write our final result in this way right here. Okay? So again, I know I'm kind of blazing through some of these examples. It's just to keep the length of the video to a short minimum. There are other resources online that might explain this a little bit better than I can, but I'm just trying to get through a lot of this material, right? So for this next one down, I'm going to go ahead and... Looks like my tablet's kind of acting up on me. I'm going to go ahead and leave this one for you guys. I'm going to go ahead and just point out here that the result that you're going to end up with here is going to be, let me do some mental math. You're going to end up here with 2 on top, cube root of 6, and then on the bottom, you're going to end up here with x squared, and then an additional copy of x squared underneath the cube root there. So that's one way to write it. Another way to write it would be to write it in the following way, where you're going to have 2 over x squared times the cube root of 6 over x squared. Okay? So again, I'm kind of blazing through that last example there, but you may want to kind of sit down with it and see if you can play with what we just talked about in the previous couple of examples and see how you can get that to work there. Okay, so let's go ahead and scroll this down and talk about how to combine radicals. So the only time you can combine radicals is if the number underneath the radical symbol is the same as each other. So if you're looking at this first example, this number underneath the radical, we actually have a name for that. It's called the radicand. You'll notice that it's both a 3 in both of these cases. So that the green light to go ahead and combine how many of these square roots of 3 you have. In the first one, I've got 2 of them, and the next one, I've got 5 of them. So if I just take 2 plus 5, that's how I got 7 of them, or 7 square roots of 3 is my result there. So if I'm trying to do an example like this next one, I'm going to look for bases or radicands that are the exact same as each other. So I'm noticing that this first root has a radicand of 2. Scanning through, I see definitely another radicand of 2 right there. So those are 2 terms that I can go ahead and combine. I'll just go ahead and box them here in blue to signify that those are like terms as each other. So the way you want to think about this is if I have 3 of these roots of 2, and then I take away 2 of those roots of 2, I'm just simply left with a single root of 2, which I'll go ahead and write over here in my answer. Okay? Let's go ahead and find another one. So another type of radicand we have here is going to be this 3. I see one there, and I see one there. So that means I've got positive 2 of them, and then I want to add on, it looks like 3 more. So if I have 2 roots of 3 plus 3 more roots of 3, that's going to give me a grand total of 5 roots of 3. Okay? And then the only other term that I have left over here is just that single root of 5, and so I'm just going to tack that on to the very end of my answer and just say plus square root of 5, and that's going to be the final result on that one. Okay? Not too shabby. Number 2, it may not look like these are ready to go, but keep in mind that we have this way of simplifying your square roots. So again, you're thinking about your perfect square numbers, and you're thinking about how to break up these radicands in terms of a perfect square number times some leftover amount. Okay? So just to give away the punchline on this, 48, I do believe that 48 can be divided by a perfect square number like 16. You could break up 48 as 16 times 3, and that's important because if we take the square root of both of these numbers, because we're taking the square root of 48, the square root of 16 is just simply going to be 4, and the leftover part's going to stay under the radical, okay? So this was 3 times that, so I'm going to write that as 3 times 4 square roots of 3. And then for that next one, let's think about how that might break up. The largest perfect square number that can go into 27, I believe, is 9. I could write that 27 is 9 times 3, in fact. And if I'm doing a square root of 27, that means I'm doing a square root of 9 and a square root of 3. That square root of 9 is going to turn into 3, and that leftover 3 is going to stay under the radical. So I'm going to have minus here 3 square roots of 3. Okay? I could clean this up a little bit because you'll notice here that out in front I've got a 3 times a 2, and we all know that that is going to make a 12 for us. So I'm going to look at this as 12 square roots of 3, take away 3 square roots of 3, and that is simply going to give me 9 square roots of 3 as our final result there. Okay? Next one down, I'm going to go ahead and you guys pause the video for a moment and see if you could take care of this one on your own. And then I'm actually going to go ahead and skip this example here in the video entirely. It would be just more of the same, breaking it up in terms of perfect cubes, doing your perfect square part, your leftover part. I know that this video is getting very lengthy, so I just want to kind of move on, okay? Here in the next example, it says rationalizing the denominator. It says here for two term denominators, multiply the top and the bottom by the conjugate of the bottom. So what's this whole business of a conjugate? Well, basically a conjugate is two expressions that are identical except one has a subtraction, the other has a plus or an addition, okay? And again, that's only for two term denominators, which is like in the second example down here. If you're looking at this first one, it's just a single term denominator, just a root 5 in the denominator there. To clear that root in the bottom, all we would need to do is simply just take this and multiply it times an additional copy of the square root of 5. And whatever we do to the bottom, we're going to have to do to the top. And the reason that we're doing that is because root 5 times root 5, well, that's just root 5 squared. And then on top, I'm going to end up with 7 square roots of 5. And the reason that that's handy is because down at the bottom, remember that a square root and an exponent of 2, those are inverses of each other. They undo each other. So we're just left here with 7 square roots of 5 all over 5 is our final result on that. Okay? Now this next, that's a two-term denominator. I've got a 3 and then I've got a root 7. And so here is where we are going to have to multiply both the top and the bottom by the conjugate of the bottom. So I'm going to write my 3, I'm going to write my square root of 7, but I want the conjugate of this expression. This already has a plus sign, so the conjugate is going to have a minus sign. So I'm going to multiply that times the bottom, and whatever I do to the bottom, I have to do to the top as well. So I'm going to say that as well up here, 3 minus the square root of 7, and then continue here, okay? So how that numerator simplify is I simply just want to go ahead and distribute in that factor of 4 into both terms of that expression. So that's going to be 4 times 3, which is going to make 12. 4 times root 7 is just going to give me 4 root 7 with that subtraction in the middle. And then down here at the bottom, these are going to be things that you're going to have to FOIL out, okay? So we have the FOIL. Okay, so this is whenever you multiply two binomials. You've got your first term times your first term. And so here for us, that's going to be a 3 times a 3. And that, of course, is going to make a 9. So we're going to write that. Okay. Change color, but Teams did not let me do that. Okay, so that's the first in FOIL. And then we want to do our outers. So that's the outer term times the outer term. That's our O. Well, that's just going to be 3 times negative root 7. So we're going to write that. Minus 3 square root of 7. We'll do our insides now. So that's root 7 times 3. Okay. Man, OneNote is really not wanting to be my friend in terms of these colors today. Okay, so there's I. So we're going to take that and say plus an additional copy of 3 square roots of 7. And then the last terms here, that's a positive root 7 times a negative root 7. So that's going to give you negative 7. Okay? And check out what happens here. Because those two middle terms, you have positive 3 square roots of 7 and then negative square roots of 3 square roots of 7. So those are going to make 0 together. So really all you have to do in the bottom is just 9 minus 7. And that's just simply going to be 2. On the top, you're going to be left with 12 minus 4 square roots of 7. And then to finish this problem off, you notice that 12 and 4 in the numerator are both numbers that can be divisible by 2. So 12 divided by 2 is 6. 4 divided by 2 is 2. And then that's square roots of 7. So there we go. I know we were kind of blazing through these examples, guys. Thank you for bearing with me. If you need to go back and watch some of this, or if you need to find some additional resources online, feel free to do that. I'm trying to get through the video. Okay? Matter of fact, how much more do we have to do here? We have a couple of additional slides here, and then we'll be all done. Okay? So, taking a look at what remains here. Okay? Some additional properties about how to translate between exponents and roots. Basically, the main idea that you need to keep in mind here is that if you have a fraction exponent, there's a way to phrase that in terms of a radical or a root. So, for example here, the number on bottom of the fraction is going to be the index on your root. So over here in this example, if I have 9 to the power of 1/2, I can rewrite this as a root 9, where the index of that root is going to be that number that was on bottom. So I can see here that that's going to be a square root, and we know the square root of 9 is just going to be a 3, so nice easy result there. This next property down generalizes this more. Just remember that that number that is on bottom of the fraction in your exponent, that becomes the index of your root. And the number that's on top of your fraction in your exponent, that becomes the exponent on your base inside of the root. Okay, so you can see how that translates over here. If I have 8 to the 2/3 power, then the number that's on bottom of the fraction becomes the index of the root, and the number that was on top of the fraction, that becomes the exponent on your base number of 8. So I can go ahead and rewrite this as the cube root of 64. And so again, just kind of thinking about how to evaluate that. The cube root of 64, just checking to see if that reduces, and I definitely think it does. The cube root of 64 is going to be 4, because it takes 3 copies of 4 multiplied together to make a 64, okay? Similarly, it works in this other direction here as well, where you can think about doing the root first and then doing the exponent after that. So if we instead, we're still going to do the exact same thing. The number on bottom of your fraction and your exponent is going to be your index number, and then the number on top is going to be the exponent. But here we're just reversing the direction of those operations, because now we're going to do the cube root of 8, which is simply just 2, and we're going to raise that to the power of 2, and that's going to simply give us a 4. So we end up with the same exact result regardless of the order that we do those operations in, okay? Real quick example here, 6. This is just translating between those two different forms. We have the radical form and then the exponential form. You definitely want to point out the index of each one of these root numbers over here. So in this first example, that's going to be a 2. So for that reason, I'm going to have 5 to the power of 1 over 2. And that's going to be your result there, okay? Over here in exponential land, in that next example, I notice that the bottom number is going to be a 2. That's how I know that the index over here in radical land is going to be a 2. And I can go ahead and rewrite this as that base of 3x raised to the number that was on top of my fraction, which here is just simply a 5. And we can go ahead and write that out if we would like. That's a square root, so there's no need to write the index number. 3 to the 5th power, you can evaluate that. That's going to end up giving you 243. Some of you do in the calculator pretty easily, and then x to the 5th on that. Okay, so just simplifying that as much as we can. On this next one, the index number is a 3, and it looks like the exponent number is a 5. So how is that going to translate? Well, I can go ahead and rewrite that as that base number of m to the power of, remember that the exponent goes on top and the index number goes on bottom in your fractional exponent, okay? So over in exponential land, I can write that. I can say 1 over m to the power of 5 over 3. And if I wanted to, I could express that using negative exponents. And to some mathematicians, it may look a little bit cleaner to write it in that way. But that's the idea. And then the last example here, I definitely noticed that the bottom number is a 3. That's going to mean that the index of my root over here in radical land is going to be a 3. And the number that's on top, of course, is the 4. So for that reason, I'm going to go ahead and say my base number of y raised to the power of 4. And then there's the whole business of that extra negative that's all the way out front. Keep in mind that that's outside this set of grouping symbols, this parentheses, so I'm just going to go ahead and write an extra negative outside there. And again, just getting some practice at translating between these two forms here. Okay, I believe this is the last example of the video, so here we go. Perform the operations and simplify. Here we have some fractional exponents, and so we're going to use our exponent rules in combination with what we just learned about fractional exponents and that kind of thing, and we're going to simplify this down. So one of the things that I notice is that on the bottom I have a set of parentheses, and then everything is being raised to the 3rd power. The operations that I see inside the parentheses are just multiplication, so I'm to raise everything inside the parentheses to that exponent. So I'm going to do that. I'm going to split this up, say x to the 1/3, y to the 1/3, and then I'll just go ahead and copy the top here, because what I want you to notice is that we've got an x over x and then a y over y. So we can now go ahead and perform our property of division, and we remember what we need to do with these exponents, right? It's going to be, if I've got x to the 4/3 over x to the 1/3, then I subtract those exponents. So that's going to be 4/3 minus 1/3, and we'll evaluate that here in a second. Let's see what those y's, same thing. I have bases that I'm dividing, so I subtract those exponents. So that's going to be a 2/3 minus a 1/3, and let's see how this simplifies. Well, 4/3 minus 1/3, that's just going to give you 3/3. X to the power of 3/3. And this is going to be 2/3 minus 1/3. That's just going to give you 1/3. And the whole idea here is that you've got 3/3 as your exponent on that. That, of course, is just 1. So we can just go ahead and write that as a single copy of x times y to the 1/3 power. And that'll do it for this set of notes. I know that was a doozy. Thank you for bearing with me. Hopefully, At some points you found it okay to just go ahead and fast forward through certain examples. Again, the idea with these videos is that they are a resource for you to do with whatever you like. You can fast forward through them, watch them at your own pace, whatever you like to do. But that's going to do it for this video covering exponents and radicals, so I hope it's been some help to you. If you have questions, let me know. But that's all I've got. Thank you very much. I'll speak to you in the next one.